be here today because acoustics is very important in Dyson. So we have more than 25 acousticians in Dyson now, working across research, which is where I'm based, in our development areas, in our motors, and more recently in our electrical vehicle development program as well. So we have very strong capability, and that is now also starting to change the way we design and develop our products as well. So 5,127 prototypes. That's how many iterations it took to develop our first product, the DC01. And this was really born out through James's belief that you have to build something and break it and find out why it doesn't work in order to really be able to then make it better and make it better again. However, over time we've become more sophisticated, our products have become more energy dense, smaller, more compact, and the interactions between the individual components, the software, the hardware, all of these things mean it's not possible to get as far as you can with just prototyping on its own. So we need to start thinking about new ways and methodologies of approaching our development cycle in order to make an impact. And acoustics is a really great way of highlighting this, because quite often, especially with people you've never worked with before, they say, oh, we'll just 6 or 4 minutes, it'll be fine, won't it? So we can go through the cycle. We have a product, we stick some media in there, and it reduces the noise. Brilliant. But in order to reduce the noise, we've had to stick a restriction in there, and that's cost us some energy. So now we then need to go through and increase the motor speed, because we need to get our performance back. But in turn, that increases the noise, we're doing more duty, and we're back to where we started almost. And so for very marginal gains, we've just wasted a lot of energy. So we can keep going through this cycle many, many times, or we can think, actually, is there a better way of approaching this? And so about 7 years ago, Fred set up the air acoustic research team within Dyson. And the idea of this team is to bring together experts in turbo machinery, fluid dynamics, and acoustics. So these are normally areas that would compete against each other for performance, or acousticians tend to turn things down. And obviously, by bringing everybody together and working towards one goal, we can start to have a kind of new philosophy in system design. And we work with our design engineers and the engineering team on ensuring we cram the technology into the right package. We make sure we've got the right performance metrics, and of course, acoustics is central to that. And so when we work in this fashion, we can have some really big results. So the first product we worked on was our second generation bladeless fan. So the first fan delivered all the performance we wanted, but it came with a few noise complaints. So on the second generation, we really went to town trying to understand what it is the customer actually wanted from this product, so understanding how the airflow interacted with them and how they perceived it. And from there we were able to optimize the exit slots. We were able to change the manifold so that we could reduce the velocities and make it as energy efficient as possible. And so while we got a 6 dBA reduction in sound power, we also were able to make this product more energy efficient. I think that's a key point, that when acoustics is embedded as part of the central philosophy, you win not just on the acoustics, but also on the energy and also on the overall design philosophy of the product. So taking a systems engineering approach is kind of central to what we do, but on our own we can't answer all the questions. And this is where we turn to our university collaborations to help us. So a good example of this is on our air blades. One of the big challenges with the acoustics of an air blade is that the sound power is driven by the high velocity jet which exits the product. And so once the sound is out, it's very hard to do anything about that. And so we had to take a real look at every aspect of this product, and we worked with Professor Anurag Agarwal at the University of Cambridge to understand as much as possible about the physics of jet noise, particularly from a very high aspect ratio rectangular jets, and couple that to our own knowledge and our own experimentation to build a performance map. And this allowed us to really pinpoint where we wanted to be in order to develop this, our latest products. And again, we've achieved a 6 dBA reduction in sound power level and a significant saving in energy. So it's all about understanding, and that's really driving how we work on our products. And to do that, we also need tools that help us at the earliest stages to understand how the products or the components interact together. And so we worked with the University of Salford a few years ago on a virtual acoustic prototyping system. And the idea behind this is that we can take individual components and subcomponents, we can characterize these, and then we can put them into a mathematical framework that allows us then to hear what that product sounds like. And this has some really powerful benefits in an industrial setting where you're trying to convince design engineers, well, look, this change, I admit it will cost you time and effort, but you can hear it now and you can see what that benefit is. But working with industry isn't just about industry benefiting. It's also useful for the universities because it helps us to pose tough, challenging questions that maybe there aren't answers for. And so in this particular project, we needed to be able to characterize the product up to 20 kilohertz. And at the time, we didn't have access to any volume velocity sources that could do this. So Salford set about developing a new volume velocity source. The graphs aren't brilliant, but basically they show commercial offering against the directivity function of the new volume velocity source. So it has much better frequency response, and it has an omnidirectional directivity plot. And these are really important for characterizing our products in the way we need to. And so here is an example of a quarter wavelength resonator. The red trace is the unfilled resonator. There you can see it has a resonance of approximately 2000 Hz. And embedding this microstructure, we can halve that and get down to below 1000 Hz. So the takeaway from this is really, if you have the right design philosophy and you embed acoustics at the beginning, and you have the right tools and knowledge, you can make some really big impacts, not just on the acoustics, but also on the other pertinent factors of performance and the energy of that product. And that's why we're really interested in being part of this acoustic network, because it will allow us to continue developing these tools with the community, but also help to train up a new generation of acousticians. And that's going to be very important moving forward, so that they're able to use these tools and help us to keep developing better products. But it's also going to bring to light the other excellent capabilities that we have in the UK that Dyson are unaware of at the minute, and will be able to start hopefully collaborating with in the future on new innovation and new areas that we haven't necessarily considered. So thank you very much for listening.